Hi everybody and welcome to the introductory lecture of the Cardiac Detection Project. In this lecture you will create and train a model which outputs a bounding box around the heart in X-ray images. As we already did in the last project, let us briefly talk about the medical background. When predicting the location of the heart via a bounding box, we get an indicator of its size and position, which can provide information about numerous diseases or symptoms. One prominent example is the cardiomyopathy, a disease of the cardiac muscle, which might lead to heart failure or blood clots. A very common symptom for this is an enlarged heart, or to be precise, left ventricle and atria, which can be observed in a chest X-ray image. In this figure you can see a heart enlarged by cardiomyopathy in the left subplot and a normal heart in the right one. Second to that, a pneumothorax or atelectasis, which both lead to collapse of the lungs, are sometimes accompanied by a change in the position of the heart, shifting it in one direction or another. In this figure, you can observe a pneumothorax and the associated change in position of the heart on the left and the condition after treatment on the right. You can beautifully see how the heart was shifted to the right. Therefore, early detection absolutely reduces the risk of severe courses and long-term consequences. In order to tackle this problem, we manually annotated the position of the heart in 469 X-ray images provided by the RSNA Pneumonia Detection Challenge, which we already used in the last project. Alright, let's look at some example images. The overall goal is that our model is able to predict those bounding boxes on all chest X-ray images. Now it's time to talk about pre-processing. As we already did when tackling the Pneumonia Classification Challenge, we downsized the images to 224 squared. Caution! When performing such an operation, you absolutely need to rescale your bounding boxes. Otherwise, your training will fail horribly. However, in this specific case, we can skip this step because we already labeled all images in the reduced resolution. As typical for X-ray images, we standardize them with the factor 1 divided by 255. In order to evaluate our model, we split the dataset into 400 train images and 69 validation images. To match the images later, we store the train and validation subject IDs. Last but not least, we compute the training mean and standard deviation to perform set normalization. In contrast to the Pneumonia Classification Project, we cannot use a pre-made dataset class in this project, but have to program one ourselves. It must be able to load the corresponding X-ray image and appropriate bounding box coordinates given a subject ID. In addition, the application of the set normalization transform and augmentation pipelines must be made possible. Regarding the augmentation pipeline, we use random contrast changes, as in this case, when augmenting the contrast of an X-ray image, we don't change the position of the heart. Additionally, we use random scaling, rotations, and translations. Of course, we need to absolutely make sure that we augment X-ray image and bounding box in the same way. We cannot simply move the image 10 pixels to the left without moving the bounding box with it. The EMG-Aug library supports us in performing those identical augmentations. Last but not least, let's talk about a model creation and training routine. We use the same base network architecture, namely the ResNet 18, where we change the input channels from 3 to 1. However, as we now want to predict 4 coordinates, we change the output dimension from 1000 to 4. This allows to predict the top left corner of the bounding boxes identified by X and Y 0 and the bottom right corner identified by x and y1. We use the mean squared error or L2 loss as loss function and the Adam optimizer with an initial learning rate of 1e-4 to train the model for 50 epochs. Alright, now it's again coding time. Please have fun working through this project and happy learning. Thank you.